Yeah, week three quiz, professor.
What problem?
Like, can you show us like how to solve these problems?
Which problem?
Like week three quiz,
What kind of problem?
like displacement vector find out.
Find out what? I don't hear you clearly. Okay, it's a up dropping signal all the time. Can you repeat again?
Like, for the week three quiz, professor.
Yeah, we see by what? What problem?
Like displacement vector calculation from using kinematics diagrams.
Kinematic diagram?
Sorry, professor.
That actually we for all the quizzes or the calculation of kinematic diagram, we all have a video for it. You have to study a lot. Okay. So far, I see the main problem for this class is that students just jump into the quiz and did not study any material. That's the problem I do see. Each week we have a lab and you just skip them and then it's very hard to teach you anything. So in each week we have the instructional material. They are video we actually for the lecture. They are also labs, and those lab actually from each other, each everyone we actually teach you all kind of material that you need for the quizzes and also for the projects. Okay, actually the programming assignments. This actually is week one. And the kinematic diagram, actually, many students did not provide a kinematic diagram. Just give me some sort of the routing of the points. It's not kinematic diagram. So here we have a whole lab on the kinematic diagram. We already teach you how to do it. Okay, you can download it. Everything that here you can download it. I show you how to download it. Just click this one. You can download the PDF files. And this in this note, by the way, what is a kinematic diagram? First, what is the study of the kinematic? Hear me? Everybody hear me? So first thing is that you need to know what is kinematic. So, okay, this word actually you should know it if you do study the high school of physics. You should know this word kinematic, okay? I'm sorry, this actually I'm not good at it. This whiteboard. So kinematic is actually related to how physics, physical things move. Okay. So in a way that in high school you do learn something like I'm sorry, this is wrong. In high school you do learn F equals ma, right? And a is acceleration. And then you do learn the kind of the how to calculate the velocity and acceleration and also displacement. These everything is related to uh, how things move, and how things move is the kinematic, what you want to study. So this diagram is related to how your robot move. You have a theta, you have the axis, you have the YZ axis, and also related joint, revolute joint, and prismatic joint. The diagram that you show here is representing how things move and how what are the control variables, theta, and also the XYZ, and also the displacement D, alpha angle if your rotation is not 90 degree with the whatever you have, you actually have a spatial angle to do rotation. Then there's an alpha angle, something like that. Okay, so the whole kinematic diagram, you need to model it and show those factors that are related to how things move. That's what kinematic diagram is all about. So we do have this video and the note to teach you how to model the kinematic diagram. So you have to watch it, okay? Because we don't have enough time to go over this every time. And I would say maybe about 1/3 or even 1/2 of the student did not submit the right kinematic diagram. So I all deduct them 10 points. And that just show me that these students did not study at all. Okay. And kinematic diagram, actually, we discussed it in class a little bit as well. And we require them, but too bad, many students just did not actually draw any kinematic diagram at all. Any question? So what I can suggest is that you have to go through every video that we have in the lab section as well. That will teach you how to set up the kinematic diagram and also teach you how to calculate or model the Dennavik-Hartenberg matrix parameters. It all included. Any questions so far? Hello, any questions so far? Okay, nothing, no question. Any questions so far? Our Monday is primarily to focus on discussing questions. Yeah, it's a question that you can raise, like, okay, what I don't know how to calculate something. We can discuss. But if you throw a question like, okay, what is kinematic diagram? That's actually too broad. And also, that just means that you haven't studied it. Okay? That's the problem. You have to study hard. The way you jump into the questions at a homework without study, that's irresponsible. Okay? That's not the way you should study in graduate school. So you need to at least set up your own plan or study plan every week. For some class like this kind of a graduate school class, how much time you need to spend? Usually, if it is a 3-unit course, you need to spend at least 3 hours per unit. So each week, 9, 10 hours of study, I would say is minimum. Okay? Because if you take 4 courses and then time 10 hours of study, you end up study 40 hours. That is typical workload of a student in college. Okay. So if you do under 10 hours of a study for a course, like 3-unit course, I would say that's too little. Okay. That's the requirement for standard student overall in college. And this one is an 8-week course. It's intensive. You are supposed to study like double the effort. So 20 hours is not a wrong thing to do. That's required because your course is an intensive course. You take 1 course or 2 courses. Each course 3 units, but it actually is not 16 weeks. You only have 8 weeks to do. So 20 hours per week for a course is also typical. Okay, that's required working amount that you need to spend the time, the kind of time you need to devote it to dedicate it to this course. Okay, we do have a lot of things to study. Any questions so far? So Krishna, what's your really question you have? I just complain a lot, but what is your the question that you something that you don't know so far? Okay, no question. We will just cover some topic. So this coming week, we are on the differential kinematic and Jacobian. Jacobian metric. Okay, Jacobian means Jacobian metric. And then also the lecture 8, inverse differential kinematic and inverse Jacobian. Okay, this actually have 4 topics: differential kinematic, Jacobian, and inverse differential kinematic and inverse Jacobian. Okay, so this different topic again, we have this dark blue slices that focus on the graduate school study, but we also have the many lab that are covering the basic part, undergraduate part. Okay, so let's look at the undergraduate part first. I originally planned to have a CS 74 for the introduction to robotics, but I did not put it there. We actually do not have that course. So from last time, we actually on the homogeneous transform metric. Okay, I teach you what it is. So these 3 transformation scale, rotate, and translate. You must understand it, okay? And then many students cannot make the Q3A. That's the displacement part. And later we cover it in class already. You have really need to understand this metric, okay? In class, we actually cover it already. So that's a homogeneous transform metric. So this week, we will move on to the next topic. For the first, for the inverse kinematic, last time we talked about it. So next one, let's look at the differential kinematic. So far, the transform metric and the so-called inverse transform kinematics, it all covers something that is static, okay? That means that we only talk about a joint and some theta that it move. So basically, it just talk about how much the angle it actually rotate, and then what is the destination location you will see. Okay, that's regular kinematic, just the displacement part and the orientation of the metric and also rotation. Okay, that's what we covered so far. Now the next topic is the differential kinematic. Differential means you take a derivative on something, okay? So when you actually take a derivative on a displacement, you get the velocity, okay? And you take the derivative on the velocity, you will get the acceleration. So first order differential kinematic is describing the velocity. Second order will be describing the acceleration. That's actually similar to regular high school physics. So here, differential kinematic is related to the velocity of the manipulator components. Okay, and differential form of a homogeneous transform can be used to examine the pulse velocity of each frames. Okay, so this will be compared to conventional dynamic vector approach. You use a metric to do calculation. Okay, so this is differential kinematic. So first thing is that you need to know about differential transforms. So we do have a H metric and a frame T. So you do take derivative on the T. You get T prime equals T plus dt. Okay, and this H is actually the metric. Okay, the metric that you take derivative. So you become a new transform form right here. Okay, and Q representing the status of the machine. So we call it state variables. So including the theta and also the displacements. Okay, that's the state variable, the control variables. And you take derivative on it, you get a new matrix. That's the kind of differential kinematic that we are looking for. So basically, your homogeneous display, the homogeneous matrix, you take derivative on it, you will give you such kind of matrix. And then including the rotational part and displacement part as well. Okay. So the rotational part, we further model it by the omega. Omega is the what? Is the d angular displacement dsdt. dc dt is your omega. Omega is angular speed. Okay. Theta is angle change. So something like that. We actually basically set up such a table. When you can perform the differential equation on the table, and you will get whatever it is. Okay. So here show you the how to calculate each component for the matrix. And the matrix will become such tables, and then we put that into case study of originally you're moving in certain frame, and then your center, your original point also rotate. Then you will end up with what kind of the speed, okay, versus your new original point. So we do have some simple Python code to actually model the differential matrix. So this one is the differential matrix. Differential kinematics. And then, I'm sorry. And then this one is the Jacobian matrix. So this differential metric is actually a basic concept of how the velocity is. The next one, what you need to look at is the Jacobian metric. So each object in a space, you may have the movement on x, y, and z. That's the 3 degrees of freedom. Besides that, you also have the yaw, pitch, and roll. What does this mean? This yaw, pitch, and roll. It means the yaw actually is rotating in this angle. So actually, yaw is rotated along z-axis. Pitch is this rotation. So pitch actually is rotating over this y-axis. And roll is actually rotating along your x-axis. Okay, so these are 3 rotation directions. So when you have an airplane, many of you are actually in the aviation college. So you have an airplane. You have movement of x, you have movement of y direction, you have movement at z direction. That's x, y, z movement. You also may have this airplane may have rotation along this. That's the so-called pitch. So pitch will see you will change. Your airplane may be pitching in this way. Okay. Okay, so that's the 6 degree of freedom. And Jacobian matrix is studying the state variable. Okay. So if you calculate your state variable theta 1 to theta 6, so actually here it can be theta, can be displacement. Okay, it depends on what kind of the joint it is. So from theta to calculate your XYZ, where your N effector is, that's called formal kinematic. The reverse kinematic is that from your destination point to calculate what control variable should be, that's inverse kinematic. Okay. And then in the week 4 project, we do want you to work on the workspace. So workspace means that you have a robot, and what is a reachable location? What is all possible XYZ? That's actually workspace. Okay. And here you say that task space because including your theta and your XYZ. So your 6 degrees of the freedom, every variable being listed in your task space or your workspace. You reverse calculate to get the right join variables. That's your control variables. That's called inverse kinematic. Okay. So let's look at a forward kinematic. When you take the velocity, you take derivative on the displacement or the control variables, you get speed. You get speed right here, the velocity of the XY direction and angular angles, angular speed angles on the solution space. And then this way, you can reverse to calculate the inverse of the Jacobian metric. You will be able to find your control variables change speed of the control variables. So that's the reverse kinematic. So first, before we do derivative, you need to know about the H function. So H function there are several state variables. Let's look at the Q1 first. So the so-called Q1 means theta 1. The first, so if you have a joint, you have a theta 1 right here. You have a theta 2 right here. So one of the variable, we call it the first state variables. Q is the status quo. So you have a status control variable Q. That means that's a theta 1. So theta 1 can be of an equation of Q1, Q2, Q3, Q4. The X can be a function of that. So each variable XYZ, when they model, they can be a function of the different variable, state variables. So usually it is a 6x1 matrix. Okay. And this 6x1 matrix can be modeled as a 6x6 matrix. When you take derivative, and now it become the Jacobian matrix. So this actually is from your state variable to calculate your workspace variables, and that require the partial differential equations. Okay, and then you can divide your Jacobian matrix into two parts. One is the linear velocity, the other one is the angular velocity. Okay, because you have XYZ change, you also have the theta phi per c change. Okay, so let's look at a simple example of this one. You have a bed. You have a robot of two angular revolute joint. Okay, so your XY can be modeled by the theta 1, theta 2, and L1, L2. L1, L2 is the length of your arm here and here. So your XY, where your XY is, can be calculated based on the equation here. And then you can think about this equation is H1. This equation is H2. So two functions. And
Thế là
these two functions, you can take a partial differential equation, and you end up with this. So this is your Jacobian metric. Okay, this is your Jacobian metric, and this Jacobian metric is used to calculate the forward kinematic. Okay, that means given a certain velocity the certain controllable change, you will end up with certain velocity on your n effectors. Okay, so singularity. Before we discuss something else, let's look at singularity. What is singularity? Singularity means that you lose some degree of freedom. Say right here, originally your equation is the second degree of freedom. But now if your θ2 is kept at 0, that means you only have one variable that is doing the effect. That is singularity. You lose 1 degree of freedom. Okay, because you fix your θ2 to be 0. In that case, here it doesn't bend. You only rotate this way. So the whole workspace is a circle. Okay, it's a circle. So that actually is losing 1 degree of freedom. And in many cases, that your matrix is not square. So you may have m times n matrix. In that case, you have to do pseudo inverse matrix if the inverse matrix is required. Okay, so anyway, so inverse Jacobian is calculated from Jacobian because it is a reverse. You get a reverse relationship, okay, of the Jacobian. So right here, show you the calculation of the Jacobian matrix. So before we jump into the Jacobian matrix, first one you need to know about the A vector and B vector, and you want to calculate the cross product. So the cross product can be calculated by this matrix. This matrix is IJK matrix AXAYAG BXBYBG. So this one will give you the cross product. So when they give you the cross product, your cross product would have IJK. And this IJK is where originally you have A, B. So your A, that assumes your A is right here. Your B is right here. Okay. Then the cross product would have a direction of crossover and then over here using the right hand rule. Okay, right hand finger this way, palm this way. And then the sum show you where your cross product is. And the calculation of the cross product is right here. To remember it is that you do forward, that is giving you AYBG minus, okay, the other one minus is going this way. It will be minus AGBY, okay. Let me show you one more time using different color. So right here, you do have IJK, you have AXB, AY, AG, BXEY, BG. So the cross product of these two vectors is that you do this way That will give you the positive term. Go this way will give you the negative term on I. So the dual is you always do it with one row and one column each time. One row and one column each time. So these two, they all have the I component. So it actually is your I component result. It's the green one minus the blue one. Okay. So by doing the similar way, each one of it, say J component have this one forward, this one, and here. Okay. That's the red one. Minus the reverse way is BG times AX here. Okay, that give you this second term here. So that's a dual you do the cross product. Okay, then you know what's cross product. Next one, you do have the Denavit-Hardenberg metric like this, okay, that we already know. So this one you would like to take derivative, and then there's a standard way to do it that's called Jacobian metric. So this Jacobian metric is they give you the formula how to calculate the Jacobian metric. So the Jacobian metric actually right here. I'm sorry, this one. There's a standard way you can calculate the Jacobian metric. So we formulate it in here. So you get it then from the Dennerby-Hardenberg metric. So you have the A1 and A2. And then you calculate the Dennerby-Hardenberg metric, T1 and T2. And from the T1 and T2, you check their O and G vectors. And the O and G vector are defined right here as they are Jacobian columns. The Jacobian columns are getting are from each one of these. This one is one Jacobian column, two different Jacobian columns. So each of the Jacobian columns right there is one row, one column, okay. And then each column, if it is a revolute joint, you are following this equation. It is a prismatic joint, you follow this equation. Okay. So different kind of a joint, the Jacobian is different. You have to see if it is revolute joint or it is a prismatic joint. And then based on the equation, you calculate the mass. And that will give you the Jacobian metric. Okay, and we summarize it into such a diagram. Okay, and the whole diagram actually, there is a Jacobian algorithm in Python example. Okay, we do give you the code already. You can download the code to study it. Okay. So that actually is where, let me show you. Okay. Okay, so this one show you how the Jacobian matrix is calculated. And they are PDF that you can download. Okay, this is the Jacobian metric slices that I just show you right now. And then there are also Python coding you can download right here. Okay, so each lab we not only giving you the study slices, but also give you the sample code. You have to download those code and look around. Okay, we all give you the sample code. Okay, that this is the Jacobian, and actually that this Jacobian is in the week 5 lab right here. Okay. Any questions so far? Any questions so far? So this, you have to go through the derivation of the Jacobian metric once and really understand what is the purpose of doing such kind of calculation. Okay. This is the inverse Jacobian. Forward Jacobian, you have to understand what is forward Jacobian first. Okay. It's coming from here. You set up the system equations for all of the joint point and then versus the XYZ, the destination variable in the workspace, and you take derivative. So Jacobian metric is a systematical way to calculate the differential equation for the derivative of your state variables. Okay, that's what it is. And these are used to calculate the velocity and the acceleration of your state variables. Any questions so far? Any questions so far? Okay, you want Krishna, can you talk? You want to talk about a week 4 assignment or what? Is that week 4 that you want to talk? Week 5, okay. So week 4, you work on what? Week 4, you work on the so-called workspace of a robot. So week 5 right here, we have 2 programming assignments, A and B. So A part, you work on this differential kinematic. So this problem is a modified problem that you see from the example that we give you. Okay, which example that you actually we show you a moment ago. This problem actually is the one that we talked about a moment ago. It is this one, the differential kinematic. It model how things move. We talked about this just a moment ago, okay? So basically, you need to watch this video in week 4. The lab video in week 4 will teach you how to calculate the problem. Okay. So that problem is a modified problem. It's actually just some parameter change. It's exactly the same as this case study. This one, this lab in week 4. Okay, we already derived everything for you, and you will calculate the velocity right here. But the number is different, of course. I would say equation is similar, but number is different. Okay. We already give you the sample code. You should modify from here. Okay, that's what I can answer you for the week 5 programming assignment. Okay. And another topic that covered this week 5 is the inverse differential kinematic or inverse Jacobian. Okay, so inverse Jacobian is that when you, after you get the Jacobian, you calculate the inverse for it, then you can use to use the velocity and angular change that you measure at the end effector backward to calculate your state variable change. So that stable variable change tell you how much you need to rotate, how much you need to rotate so that you can get to the destination. That's the purpose of the inverse Jacobian. Okay. So forward Jacobian is that based on your state variable that you know to control where you will go, that is your destination. Okay. And then inverse Jacobian is you do from your n effector expected location and speed backward to see how fast your control variable should be. Let's call inverse Jacobian. Okay. So we do have an example right here to talk about the simplified scalar manipulator and then how to calculate Jacobian. Okay, here we do have a slides and video to do that. So the G and the G linear plus plasmatic and the revolute, these are different vector that you need to calculate. It's all here, okay? It's all here. 5B, you can find the solution by yourself, okay? Similar. That actually is your responsibility to find, to study the lab by yourself. We actually give you the lab before the assignment. So 5B is the Dennerby-Hardenberg metric. We actually included in right here, okay? You should study, okay? And then the lab description is right here. So let's look at what it is required. So basically, it's a serial manipulator. So you can see that each lab or homework we have, we actually keep changing different kind of manipulators. So this kind, we do have a 2 degree of freedom serial manipulator. One is rotational revolute. The other one is prismatic revolute. So the problem is that you need to create Jacobi-Hardenberg parametric table. And we do have that in that video that above, okay? And then write a Python program to calculate the omega W0n, okay? That is the end effector frame from the original point W. Okay, so that's the program that we needed. So that this homework is working on the calculation of Denby-Hardenberg matrix, okay? So that actually is over here. You need to study this video, how to calculate Denby-Hardenberg matrix. Okay, anyway, we have two programming assignment this week for week 5, okay? And then, so some week we have one, some week we have two, okay? It depends. So this week, basically, we are covering the Jacobian and inverse Jacobian. So the inverse Jacobian, you need to understand this metric, okay? Understand this metric. It tells you how to calculate the G and the R component, okay? So you have to follow it one by one. This whole thing, this whole part, give you the whole idea of how the Jacobian matrix is calculated based on this robot models. Okay, we do step-by-step deliberation for you, and also tell you how the standard variables can be calculated and form the Jacobian matrix and calculate the inverse Jacobian matrix. Okay. Any questions so far? And after that, it's actually more typical space variable derivation in the loop in the scene. Okay. So basically here, this chart tell you the status variable that you calculate is used to control your robot arm, and your robot arm will have some sort of observation that will give you the feedback. And the feedback system go back to check with your original plane value, create the calculation and create the change of your Jacobian parameters. And then you do integral to control your variable. Okay, so this is whole block diagram for your electronics design. When you go to use a Jacobian to design a pathfinder. Okay, anyway, and the detailed Jacobian transpose is right here. Okay, anyway, and there are tons of math over there. Very complicated model. In a way, we do not expect you to be able to solve such very complicated variable or equation. So our homework is stay in a very simple part, okay? Just give you some sense of what they are. But this more detailed study is actually very complicated, okay? Very complicated. But we do not expect you can solve such a problem right now because it's too hard for you. But in the long run, there are a lot of study that you can do, okay? After knowing the basic part. And then you can model it in more detail. So basically, the purpose of your Jacobian and inverse Jacobian is that you do have a path specification. That means that you want to move your car from point A to point B. Okay, and then there's a path constraint, so you cannot go over boundary of certain places. and you cannot go over certain speed limit. Okay, given these two constraints, you go into designing of the trajectory planner, so that you need to calculate your joint spaces and Cartesian spaces to know about what is the velocity, what is the acceleration that you want to have, and also your control variables. So this is called trajectory planning, given the path simplification, and then what would be your control variable. Let me give you a simple example. A simple example is we do have a car moving from here to here. Okay. We do have car moving from here to here. So it will go from here to here. Let's assume that this line is y equals x. So given the x-axis here, y-axis right here, and you want to drive car from here to here, let's assume that it's driving from 1, to 5. Okay. So let's look at the x portion. You actually have x equals vt. Okay, let's assume this v is 1 meter per second. So it's 1. So x equals t. So x equals 0, your s is 0. X equals 1, t equals 1, your s is 1. T equals 2, your s is 2. So same thing, your y is also equal vt. So your xy is equals 1 times tt. Then your car is moving on the left on here, okay? So x equal y is your path, while your joint function x equal vt and y equal vt is your workspace variables. And then we do have a parameter called t. T is the time. So this we call it parametric equations. So you set out the parametric equations, you will be able to see where your x is. And you know that you are going on the path of y equals x. Then you can calculate how fast your x need to be changed and how fast your y need to be changed in order to make your car stay on the path of y equals x. This kind of thing we call it trajectory planning. So trajectory planning, usually you set up the equation in the parametric equation format. That means that your x, y both have the equation of t, a formula or function of t, in order to calculate the path. Is that okay? So that is the trajectory planning. Trajectory planning is that turn a specific Cartesian space trajectory into appropriate joint position reference rules. So you can calculate based on the path that you want to go on, what kind of control variable, what kind of car speed you need to drive so that you will stay on path. Okay? This is called trajectory planning. And this forward and inverse Jacobian is used to calculate this kind of the trajectory planning. Okay? Any questions so far? That's the purpose of this chapter 5. Okay, week 5, I'm sorry, week 5. It actually is this one on the inverse differential kinematic and inverse Jacobian.
Did you
Okay.
connect with somebody?
Hello? Any question? Hello? Any question? Okay. If no question, that's it for today. Any questions so far? Okay, so today I go over this forward and backward or the inverse Jacobian ones. Okay, I know there are a lot of detail, and those detail you have to really practice by yourself. Okay, because we only can cover the concept and the basic moral story about what we want to talk. Okay, but detail there are a lot of things. You have to watch video and also download a code to practice. Look at how things are, okay, then you can actually really study it, okay. But definitely you need to study before jumping to the homework, okay. Don't just go right away to homework. It doesn't work, okay. It doesn't work. It's too hard, okay. Too hard to study in that way. Okay, if no question, that's it for today, okay. See you next time. Bye bye.
Thank you.
Bye bye.